All right, hold on. Is it recording? Okay, it's recording. All right. So the this has many ways to draw these. Uh, I'm just gonna draw a couple of them. All right. So the first one is the full Lewis structure. So this is the formula we're. Oh, that's too big. This is the formula that we're doing. So first, I'm gonna draw all this carbons, and then I want to draw nitrogen on the end. You can draw this a lot of ways though. And I'm going to draw on all of the hydrogens that we have so far. And that's hold on. And that's one, two, three, four, five, six, seven, eight, 9 hydrogens. So we need 2 more because the formula is C4H11N. So we're going to make this H2 right here. And then this nitrogen is going to have a lone pair. So like, so yeah. Okay, now the line angle. We can draw this many ways as well, but if we're going directly off of the Lewis structure, we're simply going to draw the 1, 2, 3, 4 carbon and then the NH2 on the very end, which is nitro.
Is it? Sorry.
All right. So now we have 1, 2, 3, 4 carbons, and now we're going to add that nitro like that. So that's one of the ways that we can draw this line angle structure. And the line angle can be a lot of things. Wherever you put that nitrogen is really going to depend what the line angle structure is. And then we can do either one of these. I'm just going to do more line angle structures to get us more practice with that.
Yes, ma'am.
Okay. So we could also put the nitrogen right here. We could put it right here. If we put it over here, like it'd be the exact same on if we put it over in these carbons because it's a symmetrical molecule or has symmetry. All right. So if we did it like this. Oops. This has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So then this needs to have a hydrogen on that to make it 11 hydrogens. So if we did a line angle, wait. That's not. That would be how the line angle drawing would match that. And then we can also move nitrogen and okay. Instead of being right here in the middle, we can move it over 1 and put it on that carbon. So let's do that over here. And now we're going to draw in all of the hydrogens that we know. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, same as this drawing over here. So we have to add a hydrogen on that nitrogen and then a lone pair. And then this skeletal structure will be like this. Because then it would have a C right here and then C's right there. All right, down here we're looking at these different molecules here to determine their hybridization and molecular shape. So molecule 1 here, this would technically look like this. So we see that this carbon is bonded to 1, 2, 3, 4 atoms. So because it has 4 electron pair domains, it's an sp3 molecule. And now I kind of think of it as it's connected to four things. So S is 1, and then it needs to have 3 P's to add up to 4. And the molecular shape, it has sp3, all bonds, no lone pairs. So it's tetrahedral. Okay. And now if we're looking at this molecule right here, this is how it'd be like drawn in with the bond to the hydrogen. So this molecule has 1, 2, 3 electron pair domains. So that's sp2. Same thing, it's bonded to 3 things. So S is 1, and then the P has to make up the other 2 to make it 3 bonds in total. And then it has 2 bonds and 1 lone pair, which makes it bent. All right, and then looking at this molecule right here, this is technically looking at this carbon right here. So once again, drawn out, it would be like this, where this is the carbon that we're looking at. And that's bonded to 1, 2, 3 atoms with no lone pairs. So it has 3 bonds, same thing as this one up here, so it's sp2. And 3 bonds, no lone pairs, so that's trigonal planar. All right. And then this one right here, this sulfur, has 1, 2, 3, 4 electron pair domains, so that's sp3. And it has 2 bonds and 2 lone pairs, so it's bent. All right, last one here. To draw out these bonds, it has 1, 2, 3, 4 electron pair domains, so it's sp3. It has 3 bonds and 1 lone pair, so that means it's trigonal pyramidal.
Sorry, y'all.
All right. Now we're looking at these, and we're going to do the same thing, except we're skipping the hybridization step for this next question and just going straight to the molecular shape. So this molecule here is X. So let's look at X first. If we're drawing it in, there's a carbon right here that it's pointing to. And carbon's stable with 4 bonds, where for bonds, double bonds are counted as 1 or as 2 bonds. So it'd be 1, 2, 3 bonds already. So if we know that this carbon's stable and it's stable with 4 bonds, we have to add a bond to hydrogen. So we could just draw that in real quick. And then if we're determining the molecular shape, we have to think about the hybridization. So it's 1, 2, 3 bonds. So that means it's sp2, and none of them are lone pairs. So that means that X is a trigonal planar. All right, now this Y is looking at that carbon right there. And we already see all the bonds that this carbon is looking at, or bonded to, I mean. This carbon is bonded to 1, 2, 3, 4 things, no lone pair. So this is an sp3 hybridization in tetrahedral shape. Okay, this one I couldn't erase because it'd be too complicated. So we're just gonna I'm just gonna walk you guys through this. So this one's looking at the unhybridized p orbital. So to be fully hybridized, it would be an sp3, where they'd all have full bonds. So let's take it one step at a time. If we're looking at this oxygen right here, this oxygen is actually going to have lone pairs like that. So this oxygen actually has 1, let me change the color actually, 1, 2, 3 electron pair domains. So that makes it sp2. So that has 1 unhybridized p orbital because it's not an sp3, it's an sp2. Now if we're looking at this carbon right here, this carbon has 1, 2, 3 bonds connected to it, and we know that carbon is connected or stable with 4 bonds. So we know that there's another bond to hydrogen here. So now we're looking at the hybridization. Double bond counts as 1 electron pair domain. So 1, 2, 3. Same thing as the oxygen, it's an sp2 orbital, so that means it's missing a p orbital. So that's why this is circled right here. Next, we're looking at this carbon. This carbon is connected to 1, 2, 3, 4 bonds already, so we don't need to add any hydrogens. Hold on. All right, and now looking at the electron pair domains, we have 1, 2, 3 electron pair domains, because we know that a double bond is counted as 1 electron pair domain. So because it has 1, 2, 3 electron pair domains, it's sp2. Now we're going to go this way and then go around like that. So this right here, there's a carbon right here, and this carbon has 1, 2, 3 bonds shown, but we know that it's stable. So therefore we have to add a 4th bond because carbon's stable with 4 bonds to hydrogen. So now if we're looking at the electron pair domains, there's 1, 2, 3 electron pair domains, which makes it sp2. So we know that that's missing a p orbital because it's not sp3. So that's why that's circled. Now looking at this carbon right here, same thing. We see 1, 2, 3 bonds shown. It's stable, it has no charges. So we know that it has to be bonded to a hydrogen somewhere. And now looking at electron pair domains, double bond is 1 electron pair domain. So that's 1, 2, 3. Same thing as sp2, it's missing a p orbital because it's not sp3. That's why this carbon is circled. This carbon right here is connected to 1, 2, 3, 4 bonds. So we don't need to draw in any hydrogens. This carbon's not bonded to any hydrogens. So now looking at electron pair domains, we have 1, 2, 3. Same thing, that's an sp2. So we know this is unhybridized p orbital. It's right there. This carbon right here is not circled because it's connected to technically 3 hydrogens. So it would be like this, and it has all 4 bonds, and that's an sp3 orbital, so it's not missing a p orbital. And then looking at this carbon right here, same thing, we have 1, 2, 3 bonds, so we have to add a hydrogen bond. And now looking at the electron pair domains, we have 1, 2, 3, same thing, that's an sp2, so it's missing an unhybridized p orbital. This carbon here, 1, 2, 3, it's missing a hydrogen bond to make that carbon stable. And then if we're looking at electron pair domains, we have 1, 2, 3. That makes this hybridization sp2, so it's missing an unhybridized p orbital. So if we're counting them all, there's 1, 2, 3, 4, 5, 6, 7, 8. And that's why that's 8 over there. All right, now we're looking at this molecule right here. They're the exact same molecule, except this is different, where the charge is. On molecule A, it's on a carbon. On molecule B, it's on an oxygen. So oxygen would technically have, that'd be where their alone pairs are. Now, I couldn't erase it, but we already see that B is circled right here. And the reason why B is circled is because if we remember back to the rules which make one stable over the other, it's that they have closed shells. I believe it's no charges, but this one has charges. So now it depends on where the charge is at. So now we have to look at the atom that the charge is on, which is carbon versus oxygen, and then what the charge is. The charge is negative charge in both. And we know that oxygen is more electronegative, a more electronegative atom, because if we're looking at the periodic table, if I can draw it, we know that there's carbon and then oxygen is next to it. Electronegativity increases as we go across the periodic table. And because oxygen comes after carbon, we know that oxygen is a more electronegative atom. So therefore, it's more stable with a negative charge. And that's exactly what the explanation says. The explanation actually says both structures have all closed shells and only one formal charge. The more electronegative atoms are more stable with a negative charge, so oxygen is more stable with a negative charge than carbon, which is what I just explained. Okay. So down here, we're going to look at this molecule, and we're going to resonate it. And we want to keep in mind that this original structure, overall formular charge is negative. So that means these resonance have to be also negatively charged overall. All right. So starting here, we can move one of these lone pairs to make this nitrogen not negatively charged. First, I'm going to move this to the boron. So then once I move it to the boron, okay. Then we have to know where the negative charge is going. You could do the formula for the formal charge, or you could just kind of know that boron is a 3-bonder, so with that extra bond, it's going to be negatively charged. But just for like practice, let's try the formula to find the formal charge, which that is the row that it's in, or column that it's in, I mean, minus the number of bonded electrons minus the number of unbonded electrons. So for boron is in the 3rd row, so it's 3. And then how many bonds it has, which 1, 2, 3, 4. So 3 minus 4. And then how many non-bonding electrons it has, which is 0. And then when you do this math, it'd be -1, and that's why boron is negatively charged right there. All right, another way that you could do it, if we're starting back at the original molecule and ignoring this, if we're ignoring that, pretending that's not even there, the only other way we can resonate these lone electrons right here is to move it to this carbon and make that a double bond. However, if we do that, this carbon then has 5 bonds, which carbon is not stable with 5 bonds. So we have to then move this double bond right here to the oxygen, which is going to give a lone pair to the oxygen, and that's going to charge the oxygen. So let's draw that real quick. Also, there's more ways that we could draw these, but these two are what she did in the key, so I'm just going to stick to those. Also, we know that oxygen is a negatively charged because oxygen is only a 2-bonder. So that's why it needs a double bond, but because this double bond is moved to electrons, it's negatively charged. Or we can do the formula for the formal charge, which that's the column, which oxygen is in the 6th column. So that's 6. And then how many bonds it has, which is just the 1, -1. And how many lone pairs it has, which is 1, 2, 3, 4, 5, 6. So -6. So if we do this math, it's -1, which is why that's a negative charge right there. Okay, now looking at the next one, we're going to do this resonance again. So this is actually a double bond right here. So the only way that we can resonate this structure is by these lone pairs right here and then this double bond. So we can make the lone pairs go one of 2 ways, to that carbon or to this carbon right here. However, this carbon right here already has 4 complete bonds with no double bonds, so we can't resonate this carbon whatsoever. So there's no reason to even make that a double bond because you can't make carbon have 5 bonds. Also, we know that this structure right here is neutral overall, so the product of our resonance has to be neutral overall as well. Just a keynote. So the only the only other way that these electrons right here can move, if they can't move to this carbon right here, they have to move to this carbon. So if we do that, we have to then break this double bond because carbon, once again, cannot have 5 bonds, which if we put a double bond right here as well, it would have 1, 2, 3, 4, 5 bonds, which can't happen. So now we're going to move this double bond to the carbon and give that carbon lone pairs. All right, if we're going to draw the result of that. And now doing charges, we could do the formal charge calculation, which I'll show you how to do that as well. But this carbon we know needs 4 bonds. And because it only has 3 bonds and then the lone pair, we know that it's owning those electrons and not sharing it, so that's negatively charged. And this oxygen right here is stable with 2 bonds there, but it has 3. So we know that that's positively charged. And then if we did the formula to like calculate this, carbons in the 4th row, it has 3 bonds and it has 2 non-bonding electrons. So that would be -1, and that's why that's negative. And then if we did the oxygen is in the 6th row. And it has 3 bonds and 2 non-bonding electrons. So if we did that, this is actually +1, and that's why oxygen has positive charge. And also, negative and a positive cancel out, so then this whole molecule is neutral. Same as this, that whole molecule is also neutral. All right, next we're going to do nomenclature. So the first thing we have to do is we have to look at the biggest parent chain, which in this case is going to be like this. However, you could also, I believe, do this. But we're just going to stick to this for now. Let's name it real quick, or label it, I mean. And we want the smallest number. So if we named it from the other way, it would give us bigger numbers, which we don't want. So we named it the correct way from left to right. And now you have to do what we know. So this is an 8 carbon chain. Octane is 8. So we know that it's octane. We know that there's a chlorine on carbon 1. So it's 1 chloro. We see there's a methyl on carbon 2. And we know that it's 1, 2, 3. It's a propyl on carbon 4. And now if we're doing it in alphabetical order, one chloro, 2 methyl, 4 propyl octane. Okay, next we have to draw this. She gives us the name, and we have to draw the structure. So let's break this down. First, I always look for the carbon chain, which this is nonane, so that means we know we have 9 carbons. Dimethyl means that there's 2 methyls. Iodo is iodine, and bromo is bromine. So first we're going to start with drawing that carbon, or the parent chain. One, 2, 3, 4, 5, 6, 7, 8, 9. And now we can name that if we want. So I'm just going to do, or number it, I mean. So we know on carbon 4, there's a bromo. Carbon 2 is iodine. In carbon 5 and 6, there's methyl. And that would be that structure. Now let's look at this. So first, we know that cyclo is the parent chain because cyclo is always going to be the parent chain. So it's 1, 2, 3, 4, 5. Pentane is 5. So it's cyclopentane. And if we're numbering this, we're going to let's number it this way. So 1, 2, 3, 4, 5. So we see that 1 has 2 methyl groups. So it's going to be 1,1-dimethyl. 2 has a ethyl group. And 3 has a fluoro group, or fluorine. Okay. So now if we're naming it in alphabetical order, we're going to start with the ethyl. So 2-ethyl, and then fluoro, 3-fluoro, and then 1,1-dimethyl, cyclopentane. Okay, this one also I couldn't erase, but we're just going to go through this. So we have to find out which of these represent 2-methylbutane. So butane means 4, so we know that the longest carbon chain has to be 4. Well, let's look at this one right here. We have 1, 2, 3, 4. So we have the longest carbon chain as 4. However, there's 2 methyls. In this name, there's only 1 methyl. So we know that this automatically is not it. If it was 2, 3-dimethylbutane, then this would be the answer, but that's not what it's asking us to do. So now we're looking at this. This has 1, 2, 3, 4, or you could look at it as 1, 2, 3, 4, either way. And then either way, how you look at it, there's butane and a methyl on too. Now let's look at this one right here.
Your laundry's almost done.
Thank you. Thank you. For this one, we could do 1, 2, 3, 4. That's butane right here with the methyl on the second carbon. Or we can do 1, 2, 3, 4 with methyl on the second. So this one also would be an example. This one right here, same thing. 1, 2, 3, 4 with methyl on the second. Or you could do 1, 2, 3, 4 with methyl on the second. So this one also matches the 2-methylbutane. This one right here would be 1, 2, 3, 4 butane with methyl on the second. Or you could look at it like this, butane with methyl on the second. So that's why all of these represent the name, but this does not. Okay. Next, we're doing Newman projections. So this is what we're looking at, and we're particularly going to be looking at this carbon and this carbon right here. First, we're going to draw the line angle drawing in the Lewis. I like to do both, so I'm going to do that. So I'm going to do the Lewis structure first. Draw all the carbons, and then add in what I know. All right, so this is the Lewis structure of it. In the carbons that we're paying attention to, okay, well, I guess I can't highlight, but we're paying attention to this carbon right here and this carbon right here. This is X, and this is Y. And now if we're doing the dash and the wedge, looking at still these carbons, this hydrogen is up and this hydrogen is down, so this is going to be on the wedge and this is going to be on the dash because wedge is pointing up and dash is pointing down. And then bromine is just going to be in a straight line. And with this carbon right here, a hydrogen's pointing up, a hydrogen's pointing down, and then the ethyl group is on a straight line bond. So this is going to be on a wedge because it's pointing up, and this is going to be on dash because it's pointing down. Sorry. Actually, they're supposed to be opposite of each other.
We're so locked in. Lock in. She's recording. Sorry, folks. Yeah. Tuck that tiny little booty back into the chair. You're not hiding anything on the back of the chair.
Is she going crazy out there? Okay.
What?
Nothing. Okay. Oh. All right.
You want to talk about one too?
Yeah.
Great. We'll bring you some.
Just in a second. I'm almost done. Okay. Anyway, sorry for the intermission.
Sorry? Yeah, cut that out, chat.
That's not gonna
You want to hear a joke?
Nope, stop.
Sorry.
Okay.
People are gonna hate me.
And they're gonna be like, who is talking? Okay, anyways. Where's Smith? Okay.
Yeah, cut those out.
Anyways. Let's put the eyeball right here. And we're gonna look, this eyeball is gonna be looking down like that. Okay. Now for these, we're gonna draw the start of it all the same and make like an outline for it. Okay. Okay.
I gotta give some other quiz.
All right. Okay. So if we're looking here, we're looking straight at the bromine. I guess I can move the eye. Oh, I can move the eye up. Oh, a little. If we're looking at the bromine. Okay. Like that. So up is going to be hydrogen. And then down is going to be another hydrogen. And we're going to keep this the exact same on all of these. So I'm just going to put those in real quick. Wait, actually, I didn't want to do that. I lied. Okay, I'm actually going to put the bromine up here. I feel like it'll make more sense if I do that. I think you'll be able to see the anti a lot better. Okay. So then we see that directly across from bromine is gauche. That's not true. Directly across from bromine is the ethyl. So these are other. Oops. Okay. So for anti means that the biggest groups have to be anti from each other, directly anti. Which the biggest groups on this carbon is the bromine, and on this carbon is the ethyl group. So for anti, these two have to be directly across from each other. So bromine right here, that means ethyl has to be directly across right here. And then from there, these hydrogens are going to be staggered over here. Now gauche is when the two bigger groups are still staggered. So they're still staggered like this, but the two biggest groups are kind of close to each other. So we see that these two big groups, largest groups, are closest to each other. So now we can put the hydrogens on the others. Now, eclipses are when they are technically overlapping. However, we can't show that they're directly overlapping, so we're just going to put the bonds right there, and we just kind of assume that they're overlapping like that. And now we know that one of the eclipsed, we can do these a lot of ways, multiple ways to draw these, but we know that one of the eclipses, if we rotate this 60 degrees, we can get one eclipsed. And if we rotate this 60 degrees, either way, we can get another eclipse. So this constantly goes between eclipse to staggered, staggered to eclipse, eclipse to staggered. So it constantly goes here to here to, it keeps going from eclipse to staggered to eclipse. So one of the eclipse, we can put the biggest groups overlapping each other, which is actually the least stable, because it's hard for both of the groups to be right next to each other and be stable. And then from there, we can put a hydrogen there, and technically we can rotate this whole thing 60 degrees. So then this hydrogen would move up here, right here. This ethyl group will move down there. And then this hydrogen group will move right there. So those are ways to draw. And like I said, there's multiple ways to draw this, but these are just shown in the study guide. So now if we're doing them from least to most stable, we know that first when the two big groups are closest together, they're the least stable. So we know that number 3 is going to be the least stable. Where in the answer key, it's 4, because in 4, the biggest groups are near each other. And eclipses are less stable than staggered because they don't have room to actually, they're constantly repelling each other. So if we already labeled 3 on the least stable, we know that 4 has to be after that. And then staggered anti versus staggered gauche. Anti is always the most stable because the biggest groups are the farthest away from each other, so they have the most room. So we know from there, we know that 2 is the most stable, and that makes 1 right there. All right, now we're talking about the steric versus terginal strain. How me and Ajat talked about it today, and how we kind of remembered was steric is closest with staggered, S and S, steric and staggered. So in figure 1 or projection 1, it's staggered, so that's steric strain. Figure 3 is eclipsed, therefore that's torsional strain. And that's the first exam for you.